Just wait for a few more people to filter in. All right, so we're continuing on with matched asymptotic expansions, and I left it off yesterday on the matching condition, which basically says that the inner expansion and the outer expansion have to match each other. We're going to make that more precise. I'm going to write the outer expansion in a slightly different form than I did yesterday. Take the exact metric, write it as a sum over powers of epsilon. And before I had the coefficient of epsilon to the 0 just being the background g. And then I had h1, h2, and so forth. Here I'm just going to write all of those terms as g tilde n. Which are all the coefficients are functions of r. So just to make that clear, g tilde 0 is the background. G tilde 1 is h1, and so forth. Then the inner expansion, I'm going to write in a similar way. G tilde alpha beta is a sum of powers of epsilon, and these coefficients I'm going to write as g bar n, and they all depend on r bar. So similarly to what we had here, we've got g bar 0 is the object's metric, g bar 1 is capital H1, and so forth. So I'm just renaming symbols here. Now I want to do two things. I want to apply an inner expansion to the outer expansion, and an outer expansion to the inner expansion. So here I have the inner expansion of the outer expansion. So I want to take this, rewrite r in terms of r bar, and then re-expand in powers of epsilon at fixed r bar. So g tilde alpha beta is now sum over n, epsilon to the n, and then I'm expanding each of these coefficients in an outer expansion. So let me label indices p, epsilon to the p, r bar to the p, g tilde, n, p, alpha beta, where this coefficient now no longer depends on r at all. So all I've done here is I've replaced this r with epsilon r bar, and then re-expanded in powers of epsilon, which gives me these factors bar P. But let me now rewrite that back in terms of R. So I have then epsilon to the n, R to the P, G tilde, and P, alpha beta. So in this form, it makes clear that all I'm doing in the inner expansion of the outer expansion is just expanding for small r. So I'm just expanding this in powers of r. Now I want to do the same thing, but in reverse for the inner expansion. So I want to take the outer expansion of the inner expansion. So all I've done here is I've replaced r bar with r over epsilon, and then expanded in powers of epsilon at next r, because that's what the outer expansion does. So this is sum over np epsilon to the n plus p r to the minus p g bar and p alpha beta, where again these coefficients don't depend on r. So again, physically, what's happening here is I'm taking my outer expansion and just expanding, re-expanding it for small r. What I'm doing here is I'm taking my inner expansion and expanding for r much, much larger than epsilon. So at distances that are large compared to the size of the small object. Now the key thing here is I now have two expansions that are both double expansions of G tilde for small r and small epsilon. So for a sufficiently well-behaved function G tilde, the coefficients in these two double expansions have to agree with each other, term by term. So the expansions must agree term by term. Now physically again, what's happening here is if I have my small object here and say the inner expansion is valid in this region and the outer expansion, so the inner extends out to that boundary and the outer expansion extends in there, then these two double expansions you would expect to be accurate in this shaded region that's overlapping the two, the outer and the inner. And this is called the buffer region, which is the region I mentioned yesterday, where R is much larger than the small mass, but much smaller than the external length scale, which is set by capital M. So that's where you expect these two expansions to be accurate. It doesn't actually matter if they're accurate. Really, all we care about is that we have a function, g tilde, that's sufficiently well behaved that the inner and outer expansion commute. So if you do inner and then outer, you get the same result as if you do outer and then inner. So let's work out the consequences of that. So they have to agree term by term, which means g tilde and p has to be equal to g bar n plus p minus p. All right, so if I have n plus p minus p, then this becomes n p like you have over there. Is that clear? Yeah. You need a continuous, well, I mean, you have a continuous, sorry, not continuous, you have an open region satisfying this. Right, you can always choose, for example, R is square root of m, or this to the power of 1/3 or 2/3 or whatever. That will satisfy these two relationships. In general, you don't want to do the matching on a surface. The mathematics can go wrong. You really want to have an open region which allows you to actually just compare coefficients of terms in your expansions. All right, so we have this matching condition. This is our matching condition. So a consequence of that is that since g bar n plus p minus p alpha beta equals 0 for all n plus p less than 0, what that means is that there's no negative powers of epsilon in your initial starting expansion. We must have g tilde and p equals 0 for all p less than minus n. Or in other words, g tilde and p alpha beta starts at p equals minus n, meaning g tilde n is of the form 1 over r to the n plus order 1 over r to the n minus 1. So the highest power of 1 over r for the nth order perturbation is 1 over r to the n. So that allows us to draw a table g tilde 0, which recall is just the external background metric, starts at r to the 0 from that condition, plus r g1 plus r squared g2 and so on. And then g tilde 1, which remember is just h1, starts at have I given these good names? Starts at order 1 over r, because n equals 1, so the leading thing is 1 over r. And let me rename the coefficient on top, h1 minus 1. Minus 1 labels the power of r, plus r to the 0, h1 0, plus r h1 1, and so on to higher orders. G tilde 2 is h2, and because of that relationship, it starts at order r to the minus 2. Put some indices on here. And in general, the nth order term, which is the nth order perturbation in the outer expansion, starts at h minus n over r to the n, and higher order terms. Now, because of this matching condition, the things must agree order by order in epsilon and r. The columns of this table correspond to things in the inner expansion. So this, the sum of all these terms, is the 0th order inner metric, which is the metric of the small object. And then all these terms here are equal to the 1st order perturbation in the inner expansion, and these terms here add up to the 2nd order perturbation in the inner expansion. Now I want to focus on this first column for the moment. So in the first column, we have hn, write that a bit bigger, hn minus n equals the nth order term in the expansion of the inner background metric, where that expansion is given by sum over n greater than or equal to 0, epsilon to the n over r to the n. So imagine that the small object is a Schwarzschild black hole. This is just a large R expansion of the Schwarzschild metric. Say GTT of Schwarzschild is -1 plus 2m over r. So this term would be epsilon to the 0 over r to the 0, g object 0, and this term here would be epsilon over r. So remember that epsilon just counts this power of m. So put it 2 epsilon m, g object 1, and say the RR component would have higher powers of epsilon over r in it. So the leading term in the small r expansion of the outer perturbation is completely determined by the large R expansion of the inner background metric. So let's recall the Newtonian case. To get a feeling for what the terms in this expansion correspond to. So in the Newtonian case, we had phi s, the self field of the small object, the coefficient of r to the minus L minus 1. Actually, let me write it as how it's written there. Coefficient of 1 over r to the L plus 1 was determined by the multipole moment m I1 dot 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 up to I L of the small object. So these coefficients of 1 over r to some power are completely determined just by the multipole moments of the small object. And you actually have a very similar thing happening in full GR. It's a little bit more complicated. But let's think of, rather than defining those multipole moments as integrals over the Newtonian mass distribution, let's instead think of them as being defined by how they appear in the large R expansion of the gravitational potential. So we just define them to be the coefficients rather than defining them to be integrals over the matter distribution. In GR, we have definitions of mass moments mi up to L, and spin moments, I1 up to L, that are strictly in terms of the large R expansion of a stationary, or more generally quasi-stationary, drake. So these were defined by and Hansen. And so what that means is these coefficients are determined, or can be written in terms of mi up to L, si1 up to IL for L less than or equal to n minus 1. So it's a bit more complicated than it was in Newtonian physics. So there we had the coefficient of 1 over r to the L plus 1 was just in terms of the Lth multipole moment. Here the coefficient of 1 over r to the L plus 1 will be determined by all the moments up to that L. So you can think of that in terms of Schwarzschild. You don't just get the m over r at the n equals 1 there. You'll also get it for all higher powers of n in general. So say in the RR component, you'll have all powers of m over r. It's also a bit more complicated because in the Newtonian gravity, we only had mass moments. Here we've also got these spin moments. All right. Again, the key thing here, or a key thing, is that these are not defined from integrals over the interior of the body. They're just defined in terms of these coefficients of 1 over r in the large R expansion. So one consequence of that is that these definitions work perfectly well for black holes, not just for material bodies. So they apply to black holes as well as material bodies. Okay, so what does that mean? That means that H1, the first order metric perturbation, its 1 over r term that we had over there is going to be determined by the monopole moment of the small object, so just the total mass. H2 will have squares of the mass, but it will also have the mass dipole moment and the spin dipole moment, which is just actually the spin of the body. And it'll appear in this form with a Levi-Civita symbol, Sj and k over r squared. For H3, you'll have quadrupole moments, as well as products of the lower order moments. So m cubed, m squared, mi, m squared, si, all over r cubed. So ultimately, we're not that interested in what's happening right near the small object, because we're just trying to model the large-scale motion of the small object. So we're much more interested in these outer perturbations, h1, h2, h3, than we are in these perturbations in the inner expansion. And what this is telling us is that as we go to higher and higher order in the outer expansion, we see more and more structure of the small object. So at leading order, we only see the mass. At second order, we see dipole moments. Third order, we see quadrupole moments, and so forth. So the number or the amount of structure you need in your small object is determined by how high order you want to do your outer expansion. All right. So we now have this general form of the metric in this buffer region near the small object. And what I've done here is really all that needs to be done with the matching condition. It just allows us to restrict the general form of the metric perturbations, h1, h2, h3, and to express coefficients that appear in those expansions in terms of the multipole moments of the small object. So we have the general form. But we haven't yet imposed the Einstein equation. So far, this general form is not required to satisfy the Einstein equation. We now want to actually impose the Einstein equation. So to do that, I'm going to make things a bit more concrete by adopting a particular coordinate system. So let's adopt Fermi, Walker coordinates. So these coordinates are essentially co-moving with a small object. So say this is the world line gamma. Then at each point on the world line, we construct a plane that's perpendicular to the world line. So this is at, say, a proper time t, and this plane is sigma t. And the way I construct this plane is I send spatial geodesics out from the world line in directions orthogonal to the world line. I'll label the direction of that geodesic with a unit vector NA. So that unit vector is defined on the world line, but it's tangent to this plane, this orthogonal plane. So T is proper time tau on gamma, and this proper time is measured in the external background metric, not in the full metric. And we'll let r be proper distance along the spatial geodesic. So r is the distance, at a point here, r is the proper distance from the world line to that point, along that geodesic. And again, this is proper as measured in the external background metric. And now let xa be r times na. So these define coordinates on each of these planes sigma t. So these Fermi-Walker coordinates are then t xa. They've more likely, if at all, encountered coordinates of these types for geodesics gamma, not for accelerated world lines gamma. And so the acceleration will play an important role here. So in these Fermi-Walker coordinates, the external background spacetime is given by -1 times 1 plus 2ai xi plus ai xi squared plus r ti j, no, sorry, ti tj, which are functions of t only, xi xj plus order r cubed corrections. So this is the Riemann tensor of G on gamma. So you calculate the Riemann tensor of G, and then you evaluate it on the world line. That's why it only depends on T here. Then the mixed time space component is -2/3 r ti a j. It's again a function of t only. xi xj plus order r cubed. And then last, the purely spatial metric is Kronecker delta plus minus 1/3 r a I b j xi xj plus order r cubed terms. So note, on gamma, where xi is 0, the metric is just the metric of Minkowski space. So this is basically a normal coordinate system co-moving with the world line. It's not quite normal, because a normal coordinate system would require it to be Minkowski plus order r squared corrections, but here we have an order r correction. And that means the Christoffel symbols are not 0 on the world line. But it's basically as normal as you can get for an accelerated world line. So here, this acceleration is spatial component of the covariant acceleration t squared z alpha dt squared, where the covariant derivatives are defined with respect to the background metric. All right, so here I'm defining everything with respect to the background metric. But where does this world line actually live? Because I've said that near the small object, we want to use the inner expansion rather than the outer expansion. And if it's a black hole, for example, you won't actually have a world line inside of it. So the question is, how does gamma relate to some center of the small object? And we can illustrate that with a picture. So here, I'm drawing the space-time with t running in that direction. And this is the local curvature due to a small object here. So if this is how it would look for a material body, where you just have a fairly strong curvature, but nothing extreme. And that if this was a black hole, this would actually go all the way down, infinitely far down. So this is the small object here in the exact metric. So this is g tilde alpha beta on some manifold. Now we know that the inner expansion is designed to zoom in on the region just around the small object. So let me draw what the inner expansion, or the space-time of the inner expansion looks like. Something like that. So it's just zooming in on this region right here. So this space-time is space-time of the small object on some manifold of that space-time. So again, if it's a black hole, or it could be something even more exotic like a wormhole, then this manifold might have non-trivial features. Then we have the space-time of the external expansion. And this has the space-time of the external background on a smooth external manifold. And the matching condition and the two different coordinate systems we introduced, the scaled versus non-scaled distances, mean that we have some connection between these spacetimes, well, a diffeomorphism between these spacetimes. So say this diffeomorphism is phi epsilon, this one is psi epsilon, then this one will be psi epsilon composed with phi epsilon inverse. And that just corresponds to the rescaling of distances. So that takes t xa and maps it to t x bar a. Now we put the world line on this manifold, the external manifold. So this is gamma here. And we've got these coordinates that are constructed in this manifold. So Fermi-Walker coordinates are defined in the external manifold. And you can define the centeredness down here. So an example of how you would define the centeredness is you'd say that the mass dipole moment, which remember describes the location of the center of mass relative to the origin of your coordinates, you'd set that to be 0. And that would mean that your space-time here, the center of mass of that, is effectively on this world line, because the mass dipole moment defined in that coordinate system is 0. So you've got a curve up here, possibly a black hole down there, but you still have a way of identifying this gamma as the world line of that black hole. Okay, so these are the coordinates we're going to use. And now I want to go over some general features of solving the Einstein field equations in that coordinate system near the small object. So the strategy is going to be this. We're going to use the self-consistent version of the field equations. We're going to solve those equations of the self-consistent formalism. We get E of h bar 1 equal to 0. So previously, I would have had a stress energy tensor here, the point particle stress energy tensor. But here we're solving the field equations in the buffer region, so we're in vacuum. So we don't have a stress energy tensor there. Then we'll solve h bar 2, sorry, not equal to 0. E of h bar 2 is 2 times the second order Einstein tensor constructed from H1. So I'm going to solve these equations order by order in R, where we're looking at the small r behavior that was on that board previously. Then substitute the solution of that equation, or of these two equations, substitute the solution into the gauge condition, the Lorentz gauge condition, which was given by the divergence of h bar 1 plus epsilon squared h bar 2 and so forth, all equal to 0. And along with the solution to this, I'm going to substitute an expansion of the acceleration. A alpha is going to be a 0 alpha plus epsilon a1 alpha plus epsilon squared a2 alpha and so forth. So when I substitute the solution to this in here, and I substitute this expansion of the acceleration, then imposing this condition will give me equations for the A's. So we get equations for the A n alphas. And that will be the equation of motion of the small object. Okay. So in addition to the equations of motion, the output of this analysis will be two things. So one is the equation of motion for gamma. The other is the local form of these perturbations, Hn. So just from the matching condition, we had some constraints on the local form. We knew that Hn had to have the rough behavior of 1 over r to the n plus 1 over r to the n minus 1 and so forth. But solving the field equations will restrict that further. And then we will make use of this result in the next lecture. Okay. So we want to get these two things. So first, note that a spatial derivative acting on power of r, say r to the p, lowers that power of r. So we get r to the p minus 1 times spatial derivative of r. And you can easily show that this is equal to ni, the spatial unit vector. Here I'm lowering indices using just the Kronecker delta. So you can check this. So when I substitute my metric perturbations into the Einstein equation, the spatial derivatives are going to be the dominant part of the equation, because that's going to be the lowest power of r. So we can use this to simplify the equations. To simplify the Einstein equations. Need some more board real estate here. So the first term in that E, remember, was just the curved space D'Alembert box H bar n alpha beta, which was G mu nu grad mu H bar n alpha beta. And now we know that the radial derivatives, or the spatial derivatives, are going to be the dominant piece of this. So let's write this as eta mu nu plus order r corrections. So this background metric is Minkowski plus corrections. And then these covariant derivatives we can write as partial nu H bar n alpha beta plus Christoffel term times partial derivative plus a derivative of the Christoffel times H bar plus Christoffel squared H bar. So the Christoffel symbols are constructed from the smooth external metric, so they are order r to the 0. You can't have any divergent powers of r there. Similarly, this is order r to the 0. And this potentially is of order 1 over r times h bar. Because if you have a spatial derivative, it introduces an extra power of 1 over r. So this is the biggest term out of all these terms. This is just h bar. This is just h bar, and this is 1 over r h bar. But here you have two derivatives, so you potentially have 1 over r squared times h bar. So this behaves like r to the minus 2 h bar. So I can write this box operator as just the spatial part, which is just the flat space Laplacian, acting on h bar plus order h bar n over r. So the flat space Laplacian is the dominant part of this box operator. Similarly, the Riemann tensor term that appears in that E alpha beta is just over r to the 0 times h bar. Because this is the Riemann tensor of the external background, which is smooth at the world line. So altogether, this means that we can write E alpha beta acting h bar n is equal to the flat space Laplacian h bar n alpha beta plus a sum of higher order terms, which I'll write as a sum from p equals minus 1 to infinity of e p alpha beta acting on h bar n, where the index p here tells you how many orders of r are in the operator. So where e p alpha beta h bar n scales as r to the p, that's strictly proportional to r to the p times h bar. Okay. Now this is going to help us solve these equations enormously, because we can see from that form that what we're going to get is just a sequence of Poisson equations. So the Einstein field equation becomes a sequence of Poisson equations so for example, for n equals 1, we're just solving this linear equation for h bar 1. What we have is first the action of the Laplacian on the least order term of h bar 1, which was h bar 1 minus 1, and there's no right-hand side of that equation, so this is just equal to 0. And then at the next order in R, we're solving for h bar 1, 0. And now it's going to be sourced by those E superscript P terms. So we've got E superscript minus 1 alpha beta constructed from r to the minus 1, h bar 1 minus 1. So this is the order r to the minus 3 term in this equation, which I'll call star. This is the order r to the minus 2 term in star. And you can keep on going to higher order. So the last one I'll write down is the Laplacian r h bar 1, 1 being sourced by these e superscript p terms. So again, I have e superscript minus 1, now constructed from r to the 0, h bar 1, 0, and I now have one more e term, which is e to the 0, alpha, beta, constructed from r to the minus 1, h bar 1 minus 1. So this is the order r to the minus 1 equation. So let's just do some power counting to make sure that's clear to everybody. You've got r, and we bring down 2 powers of r with Laplacian, so that's 1 over r. Here we've got r to the 0. We bring down 1 more r with this e superscript minus 1, so again that's 1 over r. And then here we have r to the minus 1 and this e superscript 0. Doesn't bring down any powers of r, so this is again just order 1 over r. So you just keep solving these Poisson equations one after the other. And we can write the general form of these equations. So in general, we have the flat space Laplacian acting on the order r to the p term in the metric perturbation is equal to a sum over these e superscript p terms. So p running from minus 1 up to, or sorry, p prime running from minus 1 up to p minus 1. E superscript p minus 2 minus p prime alpha beta r to the p prime h bar 1 p prime. So this equation is the order r to the p minus 2 in the starred equation I just erased. So this is all the terms that appear at this order in the expansion. So since we have a Laplacian here, it will be useful to expand these h bars in terms of eigenfunctions of the Laplacian. So we expand h bar 1p in a basis of eigenfunctions so for example, the ordinary scalar spherical harmonics are eigenfunctions, where the Laplacian acting on the spherical harmonic is minus L plus 1 over r squared times y. So we could expand we could expand each component in scalar spherical harmonics. They are not the most convenient thing to use here, though, because we end up having lots of couplings between harmonics, and it would get pretty ugly. And also, we're working in a Cartesian coordinate system, so again, using something spherical isn't that useful. So here we're going to use the functions that I think Luke introduced. Which are n hat L, where this is the same multi-index notation that Luke introduced. So capital L means L indices, L spatial indices. So this n hat L is going to be n STF combination L, which means these are all equivalent definitions, means a product of n unit vectors and we take the STF combination of indices. Symmetric trace-free combination. So these functions n hat L are just like YLM, they're just functions on the unit sphere because a radial unit vector just points to a particular point on the unit sphere. So it's identified just by a theta and phi on that sphere. An important thing to note here is that I'm working on spheres around the small object, not spheres around the big black hole. So the theta phi I'm talking about are the theta and phi you would construct from the Fermi-Walker coordinates xi. All right. So these satisfy the same eigenequation as the YLMs. The flat space Laplacian acting on one of these functions is minus L plus 1 over r squared times n hat L. Any more chalk around here? So they do the same job as spherical harmonics. So now we write each of these coefficients, h bar n p, as a sum over these n hat L's. So we'll add another index. So I've got NPL, alpha, beta, and this now has L more indices. This is a function of T only, and then it's contracted with n hat L. So this is equivalent to an expansion in spherical harmonics. So you have a relationship h bar n p L alpha beta L n hat L is just equal to a sum over azimuthal number little m for minus L to plus L of h bar n p L m times y L m. So it's just doing the same thing, except rather than the sum over m, we now have these contractions of indices. Okay, so now when we substitute this into that equation, we get that the Laplacian acting on r to the p times h bar np is equal to sum over L r to the p minus 2. So as I said, we're always going to bring down 2 powers of r with that Laplacian. And now if you work through the calculation, what you get is p times p plus 1 minus L times L plus 1 n hat L h bar n p L alpha beta capital L t. So I encourage you to check this result. Just take this expansion and use a few identities. So use the identity here, use that ni contracted with a derivative of n hat L is 0. Another identity, and that's because n hat I partial I is just equal to a radial derivative, right? This is a radial unit vector, so derivative along that direction is just a radial derivative. And we said that these n hat L's are just defined by theta and phi on the unit sphere, so the radial derivative is 0. And everything else you should be able to work out yourself. It's only a few lines of calculation. I'll say just one more thing before wrapping up today's lecture. So we also expand E bar, or not E bar, just E superscript P, H bar, in a similar form, E, P, L, alpha, beta, capital L, constructed from H bar, n hat L. So you decompose the right-hand side of that equation in the same basis. So then this equation, no, that was not star. Let me call it star now. This equation becomes an algebraic equation for the coefficients. So star becomes r to the p minus 2, p times p plus 1, minus L times L plus 1, times the coefficient h bar 1, p, L, alpha, beta, L of t is equal to minus this sum, p prime from minus 1 to p minus 1, yes, E alpha beta L indice with index p minus 2 minus p prime L is constructed from our p prime h bar 1 p prime. And I'll define this entire source to be S alpha beta L 1 P L function of t times r to the p minus 2. So this is an algebraic relationship between the coefficients of the metric perturbation and the coefficients of the source. And we'll work out some consequences of that next lecture. All right, that's it for today. Thanks. Questions?
Okay, everybody's hungry.
No? All right, let's go for lunch.
Okay, so 2:30.